Today we are going to address the method of separation of variables to solve differential equations. In my view, it is the easiest method. In fact, most calculus students know this method and they don't know any other method, I assume. Of course, you can't always use it. You only use it when the equation is separable. And the way you recognize separable equations is if the function dy dx looks like the product of two functions. One is a function of the independent variable and the other one is a function of the dependent variable. Typical example would be y prime equals x times y, or x divided by root y. Remember, a quotient is no more than a product. So basically you could rewrite this way. Okay, so this is your g of x and this is your h of y. I didn't want to use f because this is f prime of x, so I used two separate letters for the functions. I use g and h. I don't want to use f because it can be confusing. Another example would be just y prime equals 2x, so which means h of y is 1. Or y prime is just y. You know this very well. It's like dp dt equals kp, right? You did solve this using separation of variables. Basically, what you have in this case is just this function, because g of x equals 1, and this is called autonomous. So if, let me write it down. If dy dx equals h of y, we call this autonomous. Okay, so this function dp dt, which we call this p prime, equals kp, that is an autonomous separable equation. All right, so I'm going to work out 4 or 5 examples, and hopefully each one has kind of a punchline. So I don't mean to waste your time. There will be a punchline. So the simplest one I picked, I can't make it any simpler. Well, I can call this 1. This would be probably the simplest one. Dy dx is just 1, right? So that would be the simplest, but this is simple too. So in this case, you move the dx to the right, you integrate both sides, and you get this. This is called general solution because you have, for every value of c, you have a unique solution. This is the general solution. I don't have a particular solution because there was no initial condition. Second example, I gave you just a product of x, y. So again, the y goes to the left and dx goes to the right. You integrate both sides, you get natural log of absolute value of y. Don't write y, it's the absolute value of y, because if this y is -3, you wouldn't get the natural log of 3 as an example after you plug in. And this is just half x squared plus c, okay? There is a constant c here, and there's another constant here, and I combine both constants and I just call it c, okay? We're trying to solve for y. That's how you solve differential equations, so that ln has to go away. The absolute value of y is e to this power. And you may remember from basic, I don't know, math 100, e to the half x squared plus c is the same thing as e to the half x squared times e to the c. And I call this a new c, okay? So I separate this and I call this a new c. In fact, there is a plus or minus coming in from the left-hand side. I move it to the right, and that plus or minus c, I called it a third c. So this is like a c1, c2, and this is like c3, okay? So again, this is a general solution. We'll move on. This one, it looks a little harder than the previous two. It doesn't look separable at all. I don't see g of x times h of y. But just with a little bit of work, you will recognize that it is separable. So if I fax it out an x at the bottom, I get x plus 1 times x parentheses y plus 1, which is x plus 1 over x times 1 over y plus 1. So that's your g of x, and that's your h of y. So this is separable. It's very easy to handle. This dx goes to the right, and 1 over y plus 1 goes to the left, which becomes multiplication here. So this is easy to handle. It's just half y squared plus y. This one, once again, a little bit of algebra 1. X plus 1 over x is the same thing as x over x plus 1 over x, which is 1 plus 1 over x. So I just broke it down in pieces. I cut it in here. The integral of dx is just x, and the integral of 1 over x is natural log of the absolute value of x, and of course there is another c. So I didn't finish it, but I think you can, and I hope you could finish it by yourself, because I didn't solve for y. Finish this. I'll give you a hint. You should know. The way you solve for y, you need to complete the square here, okay? So if you complete the square, multiply everything by 2 to remove this half, you get y squared plus 2y equals twice this quantity, and complete the square, and you should be able to solve for y. Because to solve a differential equation means you need to solve for y, okay? A fourth example, this is an autonomous differential equation, as I mentioned earlier. This is basically h of y, isn't it? So it looks like if a differential equation only has g of x or h of y, it looks like it is a special case of the general one, this one, right? But a special case does not make it easier, okay? In fact, this is impossible to solve using elementary methods. And I deliberately picked this one to make this point, that a special case does not make it easier, okay? I like to erase so it doesn't look messy. Okay, I'm almost there. All right. So make sure you finish this one, okay? So the cosecant of this angle is just 1 over sine of that angle. Cross multiply, you get this integral. Now you cannot solve, this is not solvable using elementary methods, and I mean calculus methods. Okay, you're not going to be able to solve it. When you study complex analysis, not only that you'll solve it, you'll also get this one for free, if I remember correctly. Kind of buy one gets another one for free. So don't even try to solve it. But this is just to make the points that an autonomous separable differential equation, which seems to be a special case of this one because g of x equals 1 here, does not make it easier. Sometimes it's easy, of course, but not all the time. Okay? So next one. This time I gave you a differential equation that is separable because that's g of x and that's your h of y, or x is your g of x and 2y squared is your h of y. You could put 2 whatever you want, but this time I gave you an initial condition, which means I gave you an initial value problem. First thing you need to do is give the general solution as we did in the first 3 examples. Cross multiply, you get to here, you integrate, you get that, you solve for y, you get this. And you can write this way if you care. I hate negative signs. Oh, no, I can't, sorry. I thought I'm going to simplify. Okay, so I got this. That's a general solution, as you know. which means infinitely many solutions based on the values of C that you pick. C is an element of R. But now we have to check the initial condition, okay? So the initial condition says that y of 2 equals 1. I called y of x so I don't confuse you. So y of 2, that means plug in 2 for x, you get this, but we also know that y of 2 is 1. So this quantity has to be 1. Cross multiply, you get c equals -5, and you got it this way. And here's what I meant to do here earlier. So I don't like negative signs. I just got rid of the negative sign and I flipped these two. Okay. So this is my my particular solution. And I'm going to ask you a question just like I did before in here to finish this problem. I would like you to think about possible, like, is there a domain? What's the domain of this function? Remember, this is f of x, okay? What's the domain of this function? Would any x work? This is a question for you to think about, okay? So next one, I'm going to give you a little harder one now. Now this looks clearly doesn't look like it is separable. I don't see a product of a function of x and another function of y. However, you see this little expression y over x, and I can make a u substitution, hoping I can turn this not separable equation into a separable equation. So if u, it's called the u substitution, if u equals y over x, cross multiply, you get y equals xu. Then I differentiate the left-hand side with respect to x, and I differentiated the right-hand side with respect to x. So d dx of y is dy dx, and d dx of this is the product rule, okay? So you get u plus x du dx. Now, I put this u plus x du dx on this side, and dy dx, if you remember, is just u, see? U minus e to the u, okay? Let me erase this. So the u cancels. So now you get x du dx equals negative e to the u. And I deliberately brought the x here to make the point for you that this is separable, okay? This is your g of u, and this is your h of x. So it's a function of u and times a function of x, okay? So that's separable. We're going to use the same trick. We're going to combine the variables, so the u's get together and the x's get together. Notice here, this minus, I kept the minus with 1 over x, okay? And I brought the dx to the right. However, in here I have e to the u. When I divide it, it becomes du over e to the u. But if you remember, 1 over e to the u is the same thing as e to the negative u, okay? So that's why I wrote e to the negative u. I don't like fractions. Then I integrate both sides. I get this. I don't have to add c yet. This one gives me this, of course. Don't forget the absolute value. Don't forget to add c. And of course, the function was a function of x. Y is a function of x. So I don't want to see u. Not you. Not you, but you. I don't want to see the letter u. I do actually want to see you. Okay, so we're going to replace u by its value. So we get this. And I like x. I have no problem with x. What I have a problem with is this letter u, okay? So that didn't change. And this is basically this. I got rid of the two negative signs completely. And then, so just pretend these two minuses went away. So we're going to take them away, okay? That still leaves me with an extra minus from here. Because once I introduce natural log on both sides, I get this quantity. So that minus is not this one. This minus is that negative sign, okay? So negative y over x equals natural log of this quantity. So it's natural log of the absolute value of x plus c. And then I brought the negative x here, and I'm done. Okay, so it looks really hard, but once you recognize that you could use some sort of a substitution, you'll be able to get it. Again, this is called a general solution because I wasn't given an initial condition, and for different values of c, you get different values of y as a function of x. So I'm going to leave you with an assignment. Okay, I'm going to give you 5 problems. I would say these 2 are really quick. You should do them with kind of closed eyes. This one looks difficult, but I'm giving you a hint. You got to use a substitution similar to something like this. It's not this, but something similar. And then you need to use partial fractions from calculus, okay? This one, it doesn't look separable at all. It's like gx minus h of y. But I would like you to use this substitution, u equals 2x minus y. I'll give you more hints. So you have dy dx equals 2x minus 5y's, and you're going to let x be 2x minus 5y's, and then you differentiate both sides with respect to x, and take it from there. And hopefully, you'll come up with something that is separable, and you solve it. And then you have a 5th one. By the way, all of these are first order. I did not give you any second order. Second order means second derivative shows up like this. So all of them are first order. Should be able to handle them a little better. The substitution I would like you to make is u equals y over x. You're going to say, why should I use y over x? In here, it was obvious. Well, in here, you just have to isolate y squared, and you will see the significance of this substitution. You should be able to finish it. So next time, we are going to address linear ODEs and homogeneous equations, and after that, we're going to do non-homogeneous equations. This is the easiest of all. I hope you'll have fun with this, and thank you so much for listening.